Fourier transform infrared, FTIR, spectroscopy, theory, principles, instrumentation, and analytical applications. Fourier transform infrared spectroscopy is a powerful, non-destructive analytical technique widely used for qualitative and quantitative characterization of organic and inorganic materials. It relies on the interaction of infrared radiation with matter, producing molecular vibrational signatures that serve as unique fingerprints for chemical identification. This video presents a comprehensive overview of FTIR spectroscopy, including its theoretical foundations, operational principles, instrumentation, sampling methodologies, and data analysis strategies, with emphasis on its application to inorganic and complex material systems. FTIR spectroscopy has become an indispensable tool in materials science, chemistry, and related disciplines for determining chemical composition, molecular structure, and phase identity. While extensively applied to organic systems, its role in inorganic materials analysis, including ceramics, minerals, thin films, and surface-modified solids, has gained increasing importance. The technique offers rapid, reproducible, and highly sensitive analysis, enabling both qualitative identification and quantitative determination of functional groups and chemical species. Its versatility arises from flexible sampling modes and advanced computational processing. Theory and fundamental principles of FTIR spectroscopy. Molecular vibrations and infrared absorption. FTIR spectroscopy is fundamentally based on molecular vibrational spectroscopy, where atoms in a molecule behave as masses connected by elastic bonds. These bonds vibrate at characteristic frequencies determined by atomic masses, bond strength, force constant, and molecular geometry. Molecules absorb infrared radiation when the frequency of incident light matches their natural vibrational frequencies. The primary vibrational modes include stretching vibrations, symmetric and asymmetric, bending vibrations, scissoring, rocking, wagging, twisting. Only vibrations that produce a change in dipole moment are IR active, making molecular polarity a key factor in FTIR absorption intensity. Harmonic oscillator model and Hooke's law. The vibrational frequency of a bond can be approximated using the harmonic oscillator model. To understand IR, it is useful to compare a vibrating bond to the physical model of a vibrating spring system. Hooke's law can describe the spring system. Consider a bond and the connected atoms to be a spring with two masses attached. Using the force constant K, which reflects the stiffness of the spring, and the two masses m1 and m2, the equation indicates how the frequency, n nu, of the absorption should change as the properties of the system change. This relationship explains why stronger bonds vibrate at higher frequencies and lighter atoms yield higher vibrational frequencies. Infrared region and wave number representation. FTIR operates in the mid-infrared region. Wavelength 2.5 to 25 micrometers. Wave number 4,000 to 400 inverse centimeters. Wave number is preferred because it is directly proportional to energy. Interferometry and the Fourier transform principle. Unlike dispersive IR spectroscopy, FTIR measures all wavelengths simultaneously using an interferometer. The resulting signal, called an interferogram, contains encoded spectral information in the time domain. A Fourier transform converts this interferogram into a frequency domain spectrum, absorbance versus wave number, enabling rapid and high-resolution analysis. Working principle of FTIR spectroscopy. The FTIR process involves several sequential steps. Infrared radiation generation. A broadband IR source, for example, a glow bar, emits radiation covering 4,000 to 400 inverse centimeters. Interferometer modulation. A Michelson interferometer splits the beam into two paths, a fixed mirror and a movable mirror. Their recombination produces an interference pattern, interferogram. Sample interaction. The modulated IR beam passes through or reflects from the sample. Specific frequencies are absorbed according to molecular vibrations. Detection. The detector records the interferogram as an electrical signal. Fourier transformation. Mathematical conversion of the interferogram yields the IR spectrum. Spectral interpretation. Peaks correspond to vibrational modes, enabling structural identification. FTIR instrumentation. Key components. Infrared source, glow bar, silicon carbide rod, or nichrome wire. Provides stable broadband IR radiation. Interferometer. Typically, a Michelson interferometer. Core component enabling multiplex, simultaneous wavelength measurement. Sample compartment. Supports different sampling modes. Transmission, reflection, ATR, attenuated total reflectance. Detector. Converts IR radiation into electrical signals. Common detectors: DTGS, deuterated triglycine sulfate, MMCT, mercury cadmium telluride. Data processing system. Controls instrument operation, performs the Fourier transform, enables spectral analysis and database comparison. Sample preparation techniques. Solid samples. KBR pellet method. Sample dispersed in IR transparent, KBR, and pressed. KBR is an ionic compound, therefore IR inactive and does not interfere with the IR spectrum. Mull method. Sample dispersed in mineral oil. Nujol. Nujol is a paraffin hydrocarbon, producing characteristic IR absorption peaks due to CH stretching and bending. These hydrocarbon bands often mask sample peaks in these regions, making it essential to use a fluorinated oil, Fluorolube, if full spectrum analysis is required. A TR technique. Direct measurement with minimal preparation. A TR is a versatile, non-destructive FTIR sampling technique used to analyze solids, liquids, and pastes with little to no sample preparation. It works by measuring the interaction of an evanescent wave, generated by total internal reflection within a high refractive index crystal, with a sample placed on its surface. Liquid samples. Transmission cells, KBR, calcium fluoride windows. A TR for rapid analysis. Gas samples. Gas cells with extended optical path length for sensitivity. Data acquisition and processing. Interferogram collection. Raw signal recorded as intensity versus mirror displacement. Fourier transformation. Conversion to frequency domain spectrum. Baseline correction. Removes instrumental artifacts and drift. Spectral interpretation. Peak position corresponds to the functional group. Peak intensity depends on the concentration, and peak shape is related to the environment/interactions of the functional groups. Quantitative analysis is based on the Beer-Lambert law. A equals epsilon CL. Enables concentration determination, but it requires calibration and a controlled path length. Spectral interpretation and functional group analysis. FTIR spectra provide a molecular fingerprint region, 1,500 to 400 inverse centimeters, and functional group region, 4,000 to 1,500 inverse centimeters. Key functional group frequencies. O-H, alcohol, 3,200 to 3,600 per centimeter, broad peak. The polar OH bond in alcohol and carboxylic acid usually shows strong and broad absorption bands that are easy to identify. The broad shape of the absorption band results from the hydrogen bonding of the OH groups between molecules. The OH bond of the alcohol group usually has absorption in the range of 3,200 to 3,600 per centimeter, while the OH bond of the carboxylic acid group occurs at about 2,500 to 3,300 per centimeter. Carbonyl, ketone. The carbonyl stretching vibration band, C double bond O, of saturated aliphatic ketones appears at 1,715 inverse centimeters. Conjugation of the carbonyl group with carbon-carbon double bonds or phenyl groups, as in alpha, beta unsaturated aldehydes and benzaldehyde, shifts this band to lower wave numbers, 1,685 to 1,666 centimeters to the power of -1. Alkene C double bond C bonds usually absorb near 1,650 centimeters to the power of -1 with medium intensity. Carbon-hydrogen bonds in saturated alkane stretch from 3,000 to 2,850 per centimeter. Primary and secondary amines can be identified by a characteristic NH stretching absorption in the 3,300 to 3,500 per centimeter range of the IR spectrum. Alcohols also absorb in this range, but amine absorption bands are generally sharper and less intense than hydroxyl bands. Ethers and epoxides typically have a strong CO stretch between 1,000 and 1,300 centimeters to the power of -1. Because this absorption appears in the fingerprint region of the IR can be difficult to assign. In addition to the CO peak, it is helpful to note if an IR spectrum has no carbonyl or OH stretch peaks to confirm it is not an aldehyde, ketone, or alcohol. Surface and advanced FTIR techniques. Attenuated total reflectance, ATR. Surface sensitive, approximately 1 micrometer depth. Minimal preparation. Grazing angle. FTIR. Thin film and coating analysis. Reflection absorption spectroscopy. Suitable for metallic and layered materials. Applications of FTIR spectroscopy. Material identification and quality control. Because of its sensitivity, accuracy, and the wide range of materials it can identify, FTIR spectroscopy is used for a wide variety of quality assurance and material identification applications in manufacturing. FTIR spectroscopy is frequently used to ensure that a sample of product contains the right amount of each of its constituent components and does not contain any contaminants that may affect the quality of its function. Polymer and composite analysis, FTIR, is a crucial, fast technique for identifying, analyzing, and quality checking polymer materials. By measuring infrared light absorption, it generates a unique molecular fingerprint that characterizes chemical bonds, functional groups, and additives. It is widely used for raw material validation, contamination identification, degradation assessment, and structural analysis. Surface characterization. While traditional FTIR passes light through a sample, transmission, surface-sensitive techniques like ATR or reflectance are designed to analyze the surface layer without extensive sample preparation. Thin film and coating analysis. FTIR is used to identify functional groups in a thin film sample. FTIR spectra confirm characteristic peaks that are affected by the changes in experimental conditions such as temperature, heating process, and pH value. FTIR spectroscopy also measures UV cure depth by monitoring the decrease in acrylate double bond intensity, typically around 810 inverse centimeters or 1,636 inverse centimeters, to determine the conversion percentage. Top surfaces cure faster due to light intensity, while bottom surfaces often show lower cure degrees due to oxygen inhibition, pigment shielding, and UV absorption. Reaction monitoring and kinetics. FTIR is an ideal tool for the accurate quantification of isocyanate compounds. Isocyanates exhibit a peak in a part of the spectrum that is usually empty, making FTIR ideally suited to the analysis of these compounds. Environmental and gas analysis. FTIR can identify and quantify dozens of different gases, for example, carbon monoxide, carbon dioxide, sulfur dioxide, ammonia, VOCs, in a single measurement. In conclusion, FTIR spectroscopy is a versatile and robust analytical technique that provides detailed insights into molecular structure and composition through vibrational analysis. Its combination of rapid data acquisition, minimal sample preparation, and powerful computational analysis makes it indispensable in modern research and industrial applications. Advances in sampling techniques and software continue to expand their applicability, particularly in complex inorganic and hybrid material systems.